Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alif Aiman bin Muhammad Sita, and my friend's name is and my group mate is my group mate name is Dilan Nabila binti Mustafa. We are from Group 6, presenting finite element analysis of the leaf spring using Autodesk Nastran.
Next is table of content. In this presentation, we are going to explain about the introduction, CAD model, FEA methodology, result and discussion, and two improvement, and lastly is the conclusion.
Okay, next I'm going to present to you about introduction of the leaf spring. So first is problem statement. The goal of conducting finite element analysis on a leaf spring is to accurately predict its structural response under various loading conditions. By analyzing stress distribution, deformation, and safety margins, FEA provides valuable insights into the spring's performance. This requires realistic modeling of geometry, material behavior, and boundary conditions. Ultimately, the analysis supports better design optimization, improved durability, and enhanced ride quality in automotive and industrial applications. Next is objectives of this research is to analyze stress distribution in the leaf spring, measure deformation to assess ride comfort and performance, and lastly, ensure strength, safety, and long-term durability of the leaf spring.
Then, we designed the leaf spring from scratch using CATIA software, and the dimension we refer to the YouTube tutorial, and it was observed that the CATIA YouTube tutorial and the journal that we refer is have slightly different in terms of the dimension, since we don't have the exactly details dimension. That's why we refer to the YouTube tutorial, and the all of the component, which is leaf, clamp, and bolts, are designed in the single part file, and then we will assembly the leaf spring together with the rod shaft and tire, and the tire was sourced from GrabCAD. And finally, we can export into set file and import in the Nastran for the simulation. And next is technical drawing. This is our technical drawing that shows the detail of the dimension for this leaf spring.
Okay, next I will talk about FEA methodology. So first is for pre-processing. Uh, Material selection. So the leaf springs are typically made from high strength material like carbon steel or alloy steel to ensure performance, durability, and load capacity. In this study, alloy steel was selected, a commonly used material in automotive application. Uh, the mechanical properties applied in the simulation are listed below. So first is density at value of 7.73 E negative 9 kilogram per millimeter cube. Next, Poisson ratio at 0.3. Young modulus at 2.05 times 10 power of 5 Newton millimeter squared. And lastly, tensile strength 2000 megapascal. So before the analysis, the 3D model must be divided into smaller elements to allow detailed numerical computation. Uh, Critical region, especially the load application areas, require finer mesh to enhance accuracy. Uh, so the mesh details that have been generated. First is mesh size at 10 millimeter. Next, number of nodes 71,807. And lastly, number of element 34,613. A mesh size of 10 millimeter provided a good balance between computational efficiency and result accuracy, especially in regions of high stress concentration near the center of the leaf spring. Next, FEA methodology. Next step for FEA methodology is setting up boundary condition. So, accurate boundary conditions are critical to simulating real-world constraints. In this analysis, both ends of the leaf spring representing connections to the vehicle chassis were fixed. This prevents any translation or rotation during simulation, reflecting actual mounting condition on a vehicle. Next is load conditions. To mimic real-life loading, an upward force of 40,000 Newton was applied at the center bottom of the leaf spring, simulating the reaction force from the vehicle axle. This setup enables accurate evaluation of stress and deflection under typical operational conditions. So next is results and discussion. This section present and analyze the result obtained from the FEA of the leaf springs. First is equivalent stress on the leaf spring. So the simulation revealed a maximum 1 meter stress at 177.2 megapascal under applied load. This value is significantly lower than the yield strength of other steels, 2000 megapascal, indicating that the material remains well within safe operational limits. The stress distribution show no regions near failure, which confirms that the current design can withstand the specified load without permanent deformation or material failure. Next is total deformation. The analysis recorded a maximum of 0.3531 millimeter. This displacement reflects the maximum deflection experienced by the leaf spring under static loading. The small value indicate that the springs retain its stiffness while allowing sufficient flexibility to absorb shocks. In suspension design, a balance between stress and displacement is crucial, and as excessive deflection could lead to material fatigue. This displacement result here is acceptable and support both performance and comfort. Next is factor of safety for the leaf spring. The minimum factor of safety calculated is at 2.034, meaning the leaf spring can support more than twice the applied load before failure. This falls within the standard engineering safety range of 1.4 to 3.0 for structural components. A factor of safety greater than 2 ensures reliability and robustness under normal operating conditions, which is especially important in automotive application where safety is critical. In order to verify the accuracy of the simulation, the FEA results were compared with theoretical values obtained from a published journal by Chayakan in 2016. Two main parameters, maximum stress and total deflection, were analyzed using the percentage error formula. Percentage error equal to FEA result minus theoretical result divided by theoretical result times 100%. So for volumetric stress, theoretical value stated at 1912.55, experimental value 177.2. For percentage error is 90.73%. For total displacements, theoretical value at 101.33. Excuse me. Experimental value is at 0.3531 and percentage error is at 99.65%. The high percentage errors observed are due to several factors. Most notably, the theoretical results were based on composite material A1 and AISI 1008, which has significantly different properties such as lower Young modulus, different density, and yield strength compared to the alloy steel used in this finite element analysis. In addition, difference in modeling assumption, machine density, and loading configuration further contribute to the difference. Despite this difference, the simulation still provides useful insights for alloy steel application and highlights the importance of material-specific analysis in FEA.
Next, I will explain about the improvement that we can get from the leaf spring and why improvement and innovation is important, because we want to improve our product and also make the product more safe. So for the first improvement, we try to simulate using other material, which is composite material, and specifically is carbon epoxy. And the carbon epoxy, we decide to simulate this material because we refer to the journal that we found. It says that carbon epoxy is more stronger than alloy steel. So we try to simulate, and we found that from the table that you can see that from the overall result, carbon epoxy performs better than alloy steel, even though alloy steel has slightly higher stress resistance, but carbon epoxy offers some of advantage, which is more flexible, low internal stress, and high safety factor. And additionally, using composite material can reduce vehicle weight and have the carbon epoxy also have the ability to absorb the vibration energy through the internal damping, and this can reduce the amount of the vibration and noise that transfer to the other parts of vehicle. For the second improvement, by using parabolic spring, as you can see in the picture, there are differences in terms of the design between traditional and parabolic spring. For the traditional, we follow the YouTube tutorial to have 7 curved flat bars that stack on top of each other, and each leaf has different length and have the same thickness. While the parabolic spring, you can see that each leaf have different thickness. And why parabolic is better than traditional? Because the design help distribute the force more evenly and allows the spring to respond more smoothly under different load, resulting in better ride, comfort, and good performance. It also can reduce the number of leaves needed and lower the risk of failure. Lastly, for the conclusion, what I can conclude from this project that we have learned how to perform linear static simulation from our lab and apply in this project by using Autodesk Nasran. Now, we understand that to perform this simulation, they have 3 main steps: pre-processing, software setup, and post-processing. And through this FEA method, we able to get the important parameters such as form measure stress, displacement, and safety factor, which can help us to evaluate the strength and the safety for the leaf spring. And based on the result, we can conclude that the component is safe because the maximum stress that we get is below the yield strength. And finally, by trying different materials and design, we can find ways to improve the performance for the leaf spring. That's all from us. Thank you.